This problem here is number 4 from section 7.3. This is a pretty involved problem, and it is possible to do with the graphing calculator, but I do find it's a little easier to do with Microsoft Excel. When you get to the problem, click over here on the right hand side and choose Open in Excel. If it does prompt you here in the corner, click Allow, then open the file. Now we have the file open. We need to manipulate it. The first thing we need to do here is sort this data in order. So if you don't know how to do that, you click Data, Sort. On column A, smallest to largest, it should default to that. So our data is now in order from the smallest to the largest. Now we need to calculate the expected z-score. This is the tricky part that the calculator can do, but it's not that easy. I'm going to show you a way to do it with the calculator, so stick around for that. I'm going to make a list of the numbers from 1 to 16. And just a little trick here, if you highlight the first 3 numbers, then drag the lower right corner, it'll populate those. And the calculation for that, if you look in the textbook, I'll bring a screenshot over. So you see this definition of this variable f that I'm going to calculate. You take each index number 1, in this case, subtract 0.375, and you divide that by n plus 0.25. Well, n is the total number, which is 16. So I'm going to use a Microsoft Excel formula here. So you type equals, and I'm going to start parentheses. I'm going to take the number 1 minus 0.375. Close the parentheses, divided by, start a new parentheses, and since n is fixed at 16, I'm going to do 16 plus 0.25. And then likewise, so that does that computation. You can double click right here, and you'll get that calculation carried out for every single number. It's a little bit of a time saver. Now that we have this list of values for f, we need to find the inverse. So these numbers here represent area under the normal distribution. We need to find the z-score that goes with each of these areas. And in your calculator, that function is inv norm. And it's very similar over here. It's just backwards. It's equals norm dot inv. And we're going to find the probability. It was right there. That's the probability number. And we need to put a comma. And for the standard normal curve, the mean is 0 and the standard deviation is 1. So you put comma 0, comma 1. Likewise, just double click here in the corner when you have that black plus, and you get those scores. And now we're going to do the final calculation here, which is equals, there's a built-in function to calculate correlation, and the 2 data sets I want to compare are the original data set right here, comma, and then the other data set is these expected normal values. And we press enter and we get a number 0.946991. So let's go back to our original question in MyMathLab and see what it was asking. So we need to compare this number, this 0.946991, to the critical value. So let's look at our table of critical values. Our critical value was 0.941. As you recall, hopefully from chapter 4, when your calculated correlation coefficient is greater than the critical value, then you say yes to the question that comes up next. Is it reasonable to conclude? We would say yes. Now be careful, you have 2 yes options here, A and D. Both of them do say exceeds the critical value. That's the consistency between option A and D. And then the difference here is therefore it is not reasonable to conclude, or therefore it is reasonable to conclude that the data come from a normal population. The conclusion is that it is reasonable now to conclude that they do come from a normal population. So we choose this option. The correlation we calculated, and if you look here, the blue text always tells me what I need to do. Round to 3 decimals. So that's 0.947. 0.947 was what I calculated. And the critical value was, just to refresh again, 0.941. And that's all you have to do for that question. I say all you do, that's actually quite a bit of work. Now let me just show you really quickly, if you did have the calculator, I'm going to show you probably a little bit of a hack here to do this without Excel. If you go to the view an example, just go ahead and click continue through all of this till you get all the parts showing. If you scroll back up to right here, the expected z-score numbers here in this column, if you look over here on my spreadsheet, they're the exact same numbers, especially if I turn these to 2-digit numbers. Now that they're two-digit numbers, you see that they're the exact same numbers. So let me show you how you do this with the calculator if that's all you have. So we have the graphing calculator open here. You're going to click Stat and Enter to edit your data. And now I'm going to type in the numbers of my data set listed right here. Alright, I have all the data entered in list 1. Now I'm going to go get my values, and so if you didn't have your Excel spreadsheet, you wouldn't have these numbers, but go over here and we're going to look at the list of numbers right here for expected z-score. Let's enter all of those numbers. Now I have all of list 2 entered, and it was just this list of expected z-score values. So I'm going to do second mode to quit out of that screen. Now before we proceed, we need to calculate regression. You may recall from chapter 4, we have to turn on the diagnostic mode. So if you recall, the way we do that is we press the second 0, and we're going to go down to the option D, to diagnostic on. Sooner we have to turn that on. So you press enter to select that option, and you press it again, and when you get done, that's when you know you have it turned on. So we're going to do stat calc, and we're going to go down and do linear regression, AX plus B, and we're going to tell it list 1, comma, list 2. And if you notice, we get our regression coefficient right here, R, is 0.94708. The reason there's a slight difference here is because I did only type in 1.777. Over here, this calculation was using all the digits of that number, so it's a little bit more precise result. But either way, when you round it to put it into MyMathLab, 0.947 is the proper number. So hopefully that explains how you can accomplish this problem. I do realize this is a very involved problem, and as such, I typically don't include this on a test. So if you have any other questions, let me know.